quick PowerPoint on radioactive decay. So we're looking at the patterns of radioactive decay. We've got here a picture of a nuclear power station, and it's being decommissioned, and that means it's being taken apart. We've talked about the problems of coal burning power stations and oil and gas burning power stations with their carbon dioxide emissions and the fact that we're running out of fossil fuels and this sort of thing. So a lot of people think the answer might be to use nuclear power stations. Well, they don't emit many carbon dioxide emissions when they're functioning. They do when you're building it, but not during the life of it, so that's good. It doesn't contribute to global warming during its life. And we're not really running out of uranium in the same way that we're running out of coal, oil, and gas. But uranium is mined, so in some senses you could think of it as a fossil fuel. But anyway, this thing is being taken apart, and that blue thing is the core. That's a radioactive core, the nuclear core of a power station. Pretty dangerous thing. A lot of uranium in there, and a lot of byproducts of that uranium which are still radioactive. Now there's this committee, this authority, the NDA, the Nuclear Decommissioning Authority, and they spend £1,000 million per year cleaning up radioactive waste. So that is pretty phenomenal. What would happen if that radioactive waste got out into the environment? Well, it would get into the food chain, it would contaminate people, and you would pretty soon know about it. The problem with it is that it stays radioactive for a very long time. Uranium has got a very long half-life. Now what's that? What's a half-life? Looking at this diagram here, we've got a piece of material, and it's got about 16 little brown spheres in there, lots of purple little atoms. Each of these spheres is an atom, and the 16 brown atoms there are unstable. They're ready to go pop. And by go pop, I mean give out an alpha particle, 2 protons, 2 neutrons. Each of those little brown spheres, those little atoms, wants to throw out its radioactivity. And once it's done there, once a single atom has thrown off its radioactivity, it becomes stable. So it turns purple in my little diagram. So I've got 16 in the first picture, and after one half-life, half of those little brown atoms, half of those unstable atoms, have gone pop, they've given off their radioactivity, and they've become stable. So in the second diagram, I've only got 8 left, 8 unstable ones. And then we go through another series, another amount of time, whatever the half-life time of this is. We've gone from 8 down to 4. And that's why it's called half-life, because you're halving the number of unstable atoms each time. So you can appreciate that over time, a radioactive substance, is going to give off less and less radiation as it goes, because its atoms are going pop. They're giving off their radiation and becoming stable. And eventually, after a very, very long time, in many cases, all of those atoms will have gone pop, and the whole thing will be stable, and it won't be radioactive anymore. Let's look at a little analogy for this. We've got 100 people, and each of them has a dice. So what's going to happen is, we've got 100 people, they've each got a dice, and I'm going to say if they roll a 6, then they go pop. So each of these people is an unstable atom, and if they roll a 6, they go pop and they become stable. And if they become stable, they're going to sit down. So we would expect, statistics tells us that 1/6 of 100 people should get 6s on their first roll, and that means that's 17 people. A 6th of 100 is 17, so 17 people sit down. So in my radioactive substance, 17 atoms go pop, they become stable, they're not radioactive anymore, they don't contribute anymore. So now we've got 83 people sitting there, standing there, 83 unstable atoms sitting there. 1/6 of them go pop on the second roll. I ask them all to roll the dice again, and 14 people sit down. And then we've got 69 people left, 69 unstable atoms left. We roll the dice again. 1/6 of them gets a 6, 1/6 of them pop, and 12 people sit down. And then we've got 57 people, 1/6 of them, they roll the dice again. Those who roll a 6 sit down. And 10 people sit down, and then we've got 47 people, and then we roll the dice again, and 8 people sit down. So I won't carry on, but what you find is the number of people sitting down each time is decreasing. In the beginning, 17 people sat down, then 14 people sat down, then 12, and 10, then 8. So the number of atoms going pop, the number of atoms giving off their radioactivity is going down and down and down. So if in a substance, this thing would be getting less and less radioactive and less harmful. Now, how long would we have to wait before it reaches a stage where it's not harmful anymore and we wouldn't have to worry about getting rid of it? Well, here's a graph that shows the half-life of carbon-14. Now, the half-life of carbon-14 is 5,700 years. So in 5,700 years, half of those unstable atoms will have gone pop, and it will be half as active as it was. 2 of those half-lives would be 11,400 years. Now 25% of them have gone pop. Sorry, 25% left. 75% of them have gone pop. And so on and so on. So we call 5,700 years one half-life, and 11,400 years 2 half-lives, and 17,100 years 3 half-lives, and so on and so on. So for carbon-14, you've got to wait a while, and for uranium it's much longer than that. For example, iridium-192 has a half-life of 74 days, so much less than carbon-14. Strontium-81 has got a half-life of 22 minutes, really quick. Now, if I were to say to you, you can hold in your hand a sample of iridium-192 or a sample of strontium-81. You haven't got a choice, one of the two. You can't say no. Which one would you hold in your hand? Iridium-192 or strontium-81? You should not want to hold strontium-81 in your hand because it's got a half-life of 22 minutes. Now what that means is it chucks out its radiation very quickly. It will go through quite a few half-lives in a day. So it will throw out the vast majority of its radioactivity very quickly, whereas iridium takes much longer. So what I'm saying is, if something's got a very short half-life, then it throws its radioactivity out very fast, and that would be very damaging for us, for biological tissues. They'd become ionized, and your DNA could get mutated, and you could get cancer and all sorts of problems. So in many ways, a short half-life is quite dangerous. Now this has something to do with how we should dispose of them. If something's going to stay radioactive for a very long time, how should we dispose of that waste? Well, I'm not going to answer that here. I'm going to go into it in more detail in the next video, but it would be good for you guys to look at this online, do some research, and find out how we should dispose of high-level waste, medium-level waste, and low-level waste. Either that or wait for the next video. Okay, quick one then. So here's your questions. We've talked about patterns of radioactive decay. That graph that you saw, you might want to slide back to that, because that you have to have that in your notes. That's super duper important, that one. Let's have a look at some questions. Have a go, pause the video, and then I'll give you the answers. Okay, let's have a look at some answers then. So carbon-14 has a half-life of 5,700 years. This is the one we saw in that graph. What fraction of its original activity will a sample have after 11,400 years? Well, 5,700 years, that's one half-life, so that's a half. But then it goes through another one, 2 half-lives. 2 5,700s are 11,400. So that's gone through 2 half-lives, okay? So it's a half of a half, and a half of a half is a quarter. So it's a quarter of its original activity. And remember it says express it as a fraction, so quarter. Seaborgium, I've never heard of that before, but I wanted to find one with a low half-life. Seaborgium-266 has a half-life of 30 seconds. What percentage this time, not fraction, but what percentage of the original activity will a sample have after 2 minutes? Okay, well, it's going to have 100% at the beginning. Now 30 seconds, it's got a half-life of 30 seconds and we leave it for 2 minutes. So how many half-lives is that? It does 1 half-life in 30 seconds, and we've got it for 2 minutes. So 30 seconds is 1 half-life. A minute would be 2 half-lives. 1 minute 30 seconds would be 3 half-lives, and 2 minutes would be 4 half-lives. So it's gone through 4 half-lives. So what is that in percentage terms? Well, 100 down to 50, that's 1 half-life. 50 down to 25, that's 2 half-lives. 25 down to 17.5, that's 3 half-lives. And 4 half-lives is down to 8.75% of the original activity. So that's how you work those out. And I've just realised I didn't put question marks at the end of my questions, and they both say question 1. I'm slipping. Hopefully that made sense to you. If not, have a look back, or have a look through the textbooks, or come and ask me. Okay, thanks for listening.